Hello, welcome back. Would like to talk to you today about lesson 6.1, day 1, which is discrete random variables. Now, this is going to be us talking about both parts of 6.1, but the first part of 6.1 has to do with us figuring out how does probability relate to, making a prediction about a given set of data. And so, excuse me, what we're going to be talking about is two separate types of variables. The first is going to be a discrete random variable. Now, the thing about a discrete random variable that's particularly noteworthy is there are separations or gaps between each of the values. So this would be what is measuring like your number of siblings. So you could have one, you could have two, you could have three, you could have four, you could have five. That's a discrete random variable. Also, the number of pairs of shoes that you own could be a discrete random variable. It takes a fixed set of possible values with gaps in between the values. For example, like I said, number of siblings or number of pairs of shoes, something like that. The other alternative would be variables that are what we call continuous. And continuous variables have no gaps and they can take on any value in an interval. For example, the thing we're going to look at is, excuse me, potentially height. So height could be a discrete random variable because your height could be 63 inches or 64 inches or 63 and a half inches. Well, you could be anywhere between 63 and 63 and a half inches. And so this is going to be a continuous random variable. So values can take on any value in the interval. So what are we going to do with this? Like I said, we're actually tying this to the concept of probability. And in probability, what we're doing is we're looking at, in a given group, the probability that a person has one sibling or two siblings or three siblings or four siblings, whatever. Well, what does that mean for us making a prediction as it pertains to a larger group? And so what we often do is we'll often make a histogram of all of the possible values. And at the bottom here go the values. And this is not to say that you have to use this for one or the other, but the example that we might use for siblings, for example, you could have certain bars here that represent, one sibling, two siblings, three siblings, four siblings, for example. And what we would run up the side here would be the probabilities of those given numbers of siblings in a given group. And what that would do for us is it would allow us to calculate what's called the expected value. And our expected value is calculated using all of the probabilities of all of the samples that are taken here. And our expected value formula looks like this. Our expected value is equal to the sum of our given value times the probability of that given value. And these should be little i's down here because it's each individual value. And so you may recognize the symbol as the symbol for mean, but when we're talking about probability, the mean is also known as the expected value. So make sure you tie those two things together. That's a huge key here. For probability, that mean is known as the expected value. Let's do a problem associated with this. Whoops. Erase that. Okay, expected value or mean there. Try to get my slide to cooperate here. So here we go. Indiana University of Bloomington posts the grade distributions for its courses online. Suppose we choose a student at random from the recent semester of this university's business statistics course. The student's grade on a 4-point scale with A as a 4 is a random variable X with this probability distribution. So kind of in your mind, you should be thinking, I know what a probability distribution is. So we're talking about a different context here perhaps when we're looking at this mean or the expected value. But we know what a probability distribution is. What would make up a valid probability model here? And so our value of 0, 1, 2, 3, 4, so remember this is grades, so this would be A, B, C, D, F. So keep that in mind. Probabilities are given. Notice we are missing one of them, right? So kind of think we're missing probability distribution number for C, but let's kind of answer these questions in order here. Write the event the student got a C using probability notation, then find this probability. So what might that mean? So how do we find this? Well, you may be thinking to yourself, well, if this is a probability model, what does it need to add up to? Well, all of these things need to equal 1. So when I took the sum of all of these probabilities, it should equal 1 because 100% of people, they got a grade, right? They got between an A and an F. And so the probability of C is going to be equal to probability of X equals 2, because that's ultimately what we're trying to find here, right? Would be equal to 1 minus 0.011 plus 0.032 plus 0.362 plus 0.457, and that's equal to 0.138. So to check your answer, you could see that all of them add up to 1, but they do. So what would it mean in words that the probability X is greater than 3 means? What does that mean? So I kind of gave you a hint up here, right, when I wrote these down, because all of these numbers really stand for a grade equivalent. So if in words, what is the probability of X greater than 3 means, that would mean the probability that a randomly chosen student gets a B or better. Sorry, that writing there. So it gets a B or better, and the probability of X is greater than or equal to 3 would be equal to 0.457 plus 0.362 equal to 0.819. Hey, I'd like to take that class. Make a histogram of the probability distribution and describe its shape. So let's make ourselves a histogram here. On the bottom, we're going to go our values. Well, what are our values in this case? Our values in this case are going to be that 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. On the side here, we need to label. So these are our values, and this is our probability. And I am going to put, so I know that my largest value is 0.457, so 0.1, 0.2, 0.3, 0.4, 0.5. Let me zoom in a little bit here. Give myself 0.1, 0.2, 0.3, 0.4, 0.5. So that when I draw my bars here, you know, if my 0 was 0.01, it's going to be pretty low here. And this one is 0.032, a little bit higher. For a 2, that was what I calculated, 0.138, so a little bit higher than 1. For my 3, I had 0.362, so let's go up here, and this is 0.457, so it's up here. So calculate and interpret the expected value of x. Now this is what's probably new here, right? Because we just had this histogram, and we're supposed to describe it. So let's describe it here. Well, what do you see? You see kind of this. So it's skewed left. Skewed. So it's skewed left, and it's got a single peak. At 4, right? So we can call it unimodal single peak at 4. That would be our SOCV kind of a deal here. Okay, so calculate and interpret the expected value of x. So my expected value of x, that was what was kind of new here from what we'd seen before. So our formula was this, and it was x sub I times p sub I. And we haven't really seen one about how to do that yet, so I'm going to show you how to do that right here. We're going to have our x sub I, so each of our values, check it out from our chart here, each of our values times its probability. So I'm going to have 3, 4, 5 products here, and then I'm going to add them all together. This is exactly how it works. So 0.011 plus 1, so this is my x sub I, p sub I, x sub I, p sub I, right? So each one. 0.032 plus 2 times 0.138 plus 3 times 0.362 plus 4 times 0.457. Now, why does this make sense? Well, it makes sense because 45.7% of the people got a 4, so it should be represented in that weight. If we weighted each one of them equally, this 0 here would be weighted the same, like one time, as opposed. So, but only 1% of people get an F, and so we weight these. Essentially, it's weighting like grades, right? Because we weight the probability based on 45.7% of the people get a 4. We should weight it like that. So that would be equal to 3.222. So what does that mean? It means that if many people, students, right? Students, let's say students. Students are chosen at random the average grade is about 3.222. Now think about it. This is not a continuous variable. So it's not a continuous variable. That doesn't mean the expected grade can't be in between two parts on the interval. So it's about a B that you would expect to get when you choose many students at random. And an important distinction to make here is students are chosen at random. That would be from this sample set here. Okay? Let's look at the second part. So the second part of this is the probability of continuous random variables. So that was a discrete random variable, right? Because you weighed 0 through 4, and that gave us a representation of grades. Well, when we're dealing with continuous random variables, we've got kind of a continuum here that we have to deal with. And what we're going to look at is standard deviation. Oops, writing in highlighter. Standard deviation of a discrete probability distribution Mr. Saris, I thought you said we were talking about continuous random variables. We are, but we can measure certain things about these probability distributions, including our standard deviation, which we remember is the average amount that something differs from the mean. We're going to represent it the same. So standard deviation here is equal to, it will be the sum of all of our x sub i's minus the mean. So the difference between our given value and the mean, like we did way back when, squared times our probability of each of them. So we're going to take the difference between the sum of the differences of our actual value and the mean squared to take into account above or below, right? Because of that, taking out that negative part, times the probability of that given event, and then take the square root. So what we've accounted for is we've accounted for the difference between it and the mean, and we've also taken into account the fact that it's squared, so we take out the negative, and we're accounting for the fact that it's a probability distribution. In that, we're multiplying by the probability. And our standard deviation squared is going to equal our variance, of course. So if they ask you about that, then what we do for a probability distribution for a continuous variable, continuous random variable, so think about this. This is kind of a reworking of what we've already done. And so this diagram is going to look super familiar to you. We go from 0 to x, and the area under our curve is always equal to 1. So if all of them are uniform, meaning all of them are the same height, it's got to be 1 over x because this distance here is x, right? And so if our area has to equal 1, well, it's the same. If it's not uniform, then what that means is it's going to look something like this, right? Well, remember this and mean, standard deviation. You should be having flashbacks, right? So we get the area under this curve. So this area equals 1 here. But what we've been doing, and it's been a little bit, but we're finding a given, a given shaded area here. We're going to use table A to find that using a z-score. And remember, our z-score is equal to x minus our mean over, let me rewrite that, x minus our mean over our standard deviation. That gives us our variation above or below our mean. Or we could use normal CDF. And remember, we have to label that one. We can't use calculator speak. So let's do an example. Excuse me. And a lot of this is going to look really familiar, right? So here we go. The heights of young women can be modeled by a normal distribution with a mean 64 inches and a standard deviation of 2.7 inches. Suppose we choose a young woman at random and let y equal her height in inches. So what type of variable is y, discrete or continuous? Kind of as we talked about before, this is going to be a continuous variable because all heights are possible. Continuous, all heights possible. Whereas you can't have half a sibling, right? So interpret the standard deviation, the heights. So remember that standard deviation was 2.7 inches. The heights typically vary from the mean. Vary from the mean. by 2.7 inches. Right, by 2.7 inches. They want us to find the probability that y is less than or equal to 63 and interpret the value. Let's draw a picture. We've got our normal curve here. How do we know that it's normal? It says it is modeled by a normal distribution with a mean of 64 and a standard deviation of 2.7. So here we go. Must label normal 64, 2.7. And we want to put our mean on there. So if our mean is 64 from here, we are actually not there. We are at 63. And when we do our normal CDF calculations and we use our table A, it is always measuring what is below unless we explicitly tell our calculator otherwise. Two ways to do this. To interpret this value, well, we're finding the probability, so we need to find this area. Remember, probability equals area. Don't forget that. Probability equals area. So if we're finding the probability under this curve, this area here is the probability. We could use the z-score. So that would be our value minus our mean over our standard deviation to give us a z-score of negative 0.37. If we go to table A, that would give us 0.3557. The other way that you could do it, remember, would be to use your normal CDF, and you need to label it. So normal CDF on your calculator. And you would have to put in your lower value because we're calculating below, and the value that we're going to, which was 63. You'd have to put in your mean. You'd have to put in your standard deviation. You would have to label every one of them. So you'd say low, high, lower, upper, lower, upper. You have to say this is your mean, this is your standard deviation, and then you could find that on your calculator, which would work. That's fine. You just have to make sure that you label it, and then you get a very, very precise answer. To interpret that value would be to say the probability there is, see if I can get a little bit closer here. There is a probability of 0.3557 that a randomly selected girl female is what the context says is less than 63 inches tall. Done. And of course they're going to ask us to do something that's between two values. And so find the probability that a randomly selected female is between 68 and 70 inches. So if I draw in my curve here, of course I label it with my 64 and my 2.7. I put in my mean of 64. I can draw in my values, and I'm going to be between 68 and 70. And as a reminder, probability is equal to area. And so I'm actually, you could use your z-scores, but I'm going to go ahead and use our calculator normal CDF functionality here. Normal CDF. And our lower is going to be 68. Our upper is going to be 70. We're going to have a mean of 64. We're going to have a standard deviation of 2.7. And of course I'm going to label lower, upper, mean. And you can use those symbols, mean and standard deviation. And that's all there is to it. And when you find that value, you interpret it as, and you would say something like this. There's a blank probability. So, if you used your z-score, what you'd get is you would get a 0.0562, so about a 5.6% chance. That's from table A, and that would be what they would accept either the table A answer on the AP test, or they would accept your calculator answer. But there's about a 5% chance that a randomly selected female is between 68 and 70 inches tall. So important things here. Make sure you've got that lower and upper mean and standard deviation labeled. But really, this is kind of a reprise of what we've done in the past with our normal distribution. Now we're tying it to expected value, and so that's kind of where we're at with our probability and our expected value of discrete and random, discrete and continuous variables. All right, guys. So thanks for watching, and we'll see you next time.